It's my great pleasure to introduce the three winners of the 2014 Kavli Prize for Nanoscience. They are Stefan Hell, Thomas Eberson and John Pendry. Now, the contributions you've made to the fields of microscopy have been transformative in many ways. And I think what's striking about the work that you've done is that all of the objectives, all of the questions you've been asking and testing and making things have been questions that were seemingly impossible. Perhaps you could tell us about the limitations of microscopy that were once thought to be impossible, but that you found a way around them.
Well, light microscopy has been around for a long, long time, but at the end of the 19th century it was discovered that you cannot get sharper pictures than a certain value, so half the wavelengths of light. And this was accepted throughout the 20th century, so people accepted this as a fact and didn't think about the fact that it could be possibly improved while retaining the concept of focusing light. Now, retaining focusing is very important if you want to look, for example, inside living cells or living tissues, if you want to see living things in particular, or proteins very specifically. And so I've been questioning whether it's really not possible to go beyond that barrier, and eventually found a way to get much sharper pictures and get a level of detail that was not anticipated.
Was it the challenge of the impossible that drove you? I mean, we have had microscopes that can look, electron microscopes can look much smaller than light microscopy, but it was making things in the light wavelength that was important.
Exactly, exactly. So I was driven actually by curiosity. I'm trained as a physicist, and definitely not just in optics or in any other subfield of physics, so I had a general view of the problem. And I was just curious to see whether it's possible to find a physical solution, whatever that is, to get beyond the barrier. And initially I was not just interested in improving it for biology or for the life sciences, but I just want to find out a way, if it's possible, to come up with a light microscope that has much sharper pictures. And eventually it turned out to work extremely well for fluorescence microscopy, which is relevant to the life sciences in particular.
And it's been kind of transformative in a way that I've spent half my life looking down microscopes, but then you go out and you invent a new way of doing it. How has it been adopted?
Very well. By now, all the big companies offering a light microscope, fluorescence light microscope, offer a so-called super resolution option as their flagship product, and it's now accepted in many labs. It's used in many labs. New discoveries are being made, and we get new insights as a result of the fact that we can see things in a cell at a higher level of detail.
Do you see yourself, in fact this is to all of you as well, but do you see yourself as physicists who are working in technologies which are going to drive the life sciences? Because the whole history of microscopy has been people making better lenses so that people like me could look at things more closely. John, is that something that's been driving you to help biologists out?
No, I think I go along with what Stefan said. I'm very happy that should they be helped by what I do. They haven't been so far. But we're all driven by curiosity, I think, and very often the spark for what we do is the unexpected, and so it's very important for a scientist to be very observant. And when you see something which is anomalous, to use somebody else's word, no bigger than the size of a man's hand, you shouldn't let it pass by, because behind that anomaly you may find something very surprising. And I think we all three of us have had that experience. I certainly have.
Tell us about your perfect lens, because lenses through history have been pretty good and getting better and better, but perfection, and that's a high bar to set.
It is, yes, but I'm a theorist, so that's okay. Light, there's two sorts of light. There's the light which can easily escape from an object or a surface, and that's the light which we use in microscopy. But the other sort of light is what we call the near field. It's called that because it sticks to the surface and doesn't escape. And that second sort of light contains the information which is necessary to have perfect resolution. And what I was able to do was to find a way of unsticking that light from the surface to bring it to be part of the image.
See, this is when I get confused, because in the world of nano-optics and in the world of physics in general, you talk about use concepts like unsticking light. One of the things when I was reading up on your work that made me scratch my head a lot was how you've effectively devoted a large chunk of your career to making things go through holes that are smaller than them.
Yes.
Can you explain that and how
Yeah,
it works?
but it ties actually nicely in with what John just said, in that, well, there was an accidental discovery, but again, a key element in getting light through very small holes is the fact that the light is piling up on the surface. And the second kind of light that John was just talking about plays a key role there. Without that, we wouldn't see the kind of physics that we are seeing in the large transmission through tiny holes. And so light gets trapped on the surface, and the surface acts like an antenna for, like a radio antenna, except this is a light antenna, and it piles up above the holes, and it's like as if it was focused on the hole. And then, even though the amount of light falling on each hole is tiny, the whole surface is collecting the thing, and so it builds up, and then you get very large transmission through the holes. Much larger than what theory had predicted until then. And then again, it's what Stefan was talking about. There was a well-known theory done by Hans Bethe in the 1940s that said that very little light could get through such small holes. And that's why nobody believed what I saw. And I am not an optics person, I'm not even a physicist. So this was just a sort of an accident along the way, you know, and curiosity driven, and I tried to understand what was going on, and you know, one thing led to the next. And that's why I'm here today.
The prizes, the Kavli prizes, and almost every scientist that I've ever spoken to across my career have said, driven by basic research, driven by curiosity, and just asking the most fundamental questions. In your case, is trying to defeat the impossible. But I think compared to the other Kavli categories, yours is a field that has had a most technologically transformative effect on other sciences. Your curiosity questions, your research has changed the way other scientists behave. Is that part of your mindset when you set up your experiment? You describe yourself as a theoretician, but you know, you change how other scientists work.
Yes, I think that's a philosophical comment, but I think it relates to a lot of physics-based science that for a long time in the 20th century, physics thought of itself as the perhaps not the queen of the sciences, but maybe the king of the sciences, with the nuclear physics and the semiconductors and so on. But I think the role of physics has transformed a little since then into being a servant of other sciences. So many of the technologies in biosciences are physics-based. And in fact, when I was a research student, my office looked out over what looked like a garden shed, but was in fact the hut where DNA, the mystery of DNA, was unraveled by Crick and Watson.
It was a garden shed.
Yes.
Thomas, what you were just describing there, the ability of the surface of these materials with nano-sized holes that can trap light, how has that become a technology that microscopists and other researchers can use?
Microscopy, I don't think that's probably not the most important use, because there are other techniques for that. I think it's more for, except perhaps the concepts that one can play with. There are some form of microscopy who play on that, play on this capacity to trap the light on the surface of metals, but it's more in, I think the impact is more in sensing. That's the first large area where people actually, there are commercial products again that use these principles. There are a lot of labs that use them, not commercially, but have asked us, for example, or other groups to make structures that are based on what we found. And then there is also the realization that this is not just my contribution, but this part of the events that triggered this interest in these surface, light trapped at surfaces, where you can build all kinds of light circuitry in a very miniaturized way, and devices which are beginning to impact on telecom industry, devices, internet signal transfer, data transfer, because it's energetically it's a very high energy consuming process, the internet, contrary to what everybody believes. It consumes a very large amount of the world's electricity. And so, because it uses electrons, so the electronics you can just feed your laptop and see how hot it gets, then you know there's a lot of energy consumption. And so the idea is to try to replace some of the circuitry with optical circuitry. and to process information. And that's where I believe that's a long-term process, but where one of the significant uses will be of this sort of what we call surface plasma photonics.
That does sound very much like the part of the drive is application. It's tech transfer from basic research.
Well, that always is. I think today most scientists think of that. I think, joining what John was just saying, that we do think of. I mean, we are motivated by curiosity, by trying to understand the laws of nature, but of course we think, oh, this could be used for that. We have to justify it to get grants, so we have to try to see how it fits in. We're always happy to have interactions with industry people or people who want to use this. And because they often they see applications that we can't even foresee, because we don't know the challenges. For example, in the telecom industry, I had no idea that the servers use so much energy until I was invited to a conference where this was discussed, and then I knew why I was at the conference, because it was they wanted to learn more about what I was doing to see how that could be integrated into to help them solve their problems.
Stefan, you describe yourself as a physicist who has transformed biology. John, you're a theoretical physicist?
Yes.
How would you describe yourself?
I'm a physical chemist.
A physical chemist. And all of you have worked together in the past, you've published papers together, you've been to conferences together. How is it that these slightly different fields can overlap so significantly?
I think that's the strength of basic science, that if it's really basic, it reaches across many disciplines and its influences spread far and wide. That's its power, but also in some ways it's its disadvantage, because sometimes it's not noticed because it's spread over such a wide area. And I think one has to be aware of that when selling science to the government.
Thomas, tell me the story you were just mentioning before we started this about the first time you came across Stefan's work.
I invited Stefan to our institute to give a talk, and he gave this beautiful talk on the research for which he's getting the Kavli Prize. And I was very skeptical. I asked him some questions at the end. I couldn't quite believe what he had just presented, because it seemed that I couldn't see how you could break Abbe's limit, which is what he has broken. But of course, as I thought about it more and read about it more, I was convinced at the end.
Were you confident that when you were being challenged, when you're being invited to someone else's lab and you present your work and he says, yeah, I don't believe it?
Well, I mean, at least I had some, I would say, acceptance for the notion that people were very doubtful. I think there are good reasons for that, because it's kind of unusual, and throughout the 20th century there have been several proposals for overcoming the diffraction barrier, but none of them really worked. So at the end of the day, they turned out not to be practical. Mm-hmm. And so there were, of course, reasons to doubt whether you can make it work. And there was a lot of work sorting out subtle details, problems, in order to make sure that it works the way you think. Mm. And initially it was just a proposal, but fortunately it worked out. I think the reason why it worked out was that the physical concept behind it was very strong. So initially, after I realized that it could be done that way, I thought about possible flaws, like we all do if we have new ideas. And I thought many, many weeks about, are there any flaws, anything that I may have missed in this concept that may in the event spoil the whole idea.
And this is when it's theoretical. This is
when it's theoretical. Yeah. Yes. Initially, it was just a proposal and it was there as a proposal for a couple of years. This has something to do with the fact I didn't have my own lab, I didn't have the funds to do it. So it was there, but I couldn't find the real flaw. I found all the arguments that would put against the concept. In the end, I could somehow show that they are not, say, profound, and so they could be surmounted by technical advancement and so on. And this is the reason why I moved on with the development and decided to go through with it and to develop it and to show that it works, and that turned out to be right.
Was part of the motivation, this concept, the Abbe limit, was a physical limitation that you wanted to beat? You could see a way I think that it could be broken?
Yeah, from my view, the problem was seen from the wrong angle, so to speak. I mean, people thought in those days that in order to come up with a sharper picture using focused visible light, you definitely have to do something about the way the light is focused, or the light is concentrated in space, to be very precise. And they try to squeeze it through tiny holes, and this is a concept, but it has strong limitations, especially for life science applications. But I thought it's better to take on a different view. perceive the object that you look at, the molecules that you look at, as a part of the image formation. So if you try to play with them, say put them in different states, then you can make them discernible. So you don't have to change the way the light is focused in order to make a sharp picture. You can play with the object that you look at, put the molecules in different states to make them discernible. Because in the end, getting a sharper picture is about making things discernible. And once you have to discern them, it's fine. You get the image. Doesn't matter whether it's by focusing or by a state transition. So the state transition turned out to be the key to getting a sharper picture in my case.
But the key thing about the technique, your technique, is that you can, I mean, from a biological point of view, is you can use it on living tissue.
That's right.
So that interaction, that light interaction, is happening with cells that are alive, which is
right.
what biologists need.
Exactly, exactly. This is because, say, freely propagating light, visible light, is very benign to living cells. There's little interaction apart from the interaction with the molecules that we want to see, which are, in my case, the fluorescence molecules, the molecules that are attached, for example, the protein of interest. And this is what biologists usually do. So 80% of the applications of microscopy in the life sciences are fluorescence microscopy, because you see proteins specifically. And so we play actually with the states of the fluorescent molecules just to make them discernible, and that's the solution to the problem in my case.
What do you see as the next big challenge? I want to ask you Stefan, first, but also you guys too. But what's the next big challenge? The thing that is really driving you at the moment?
I think the concept is very well understood. I mean, there are very many ways actually to play this concept of on-off. I think it's still important to improve the method such that it gets faster, more sensitive, higher resolution. And the reason for that is that the current limits of performance that we have, and the performance is getting better and better year by year, determines what we can discover in the life sciences. So if you make it, say, 5 times faster, we can see 5 times faster processes in biology, in basic medical science, and that means we may discover something that we couldn't have seen before. So the performance that we have now in the light microscope is right at the cutting edge of discovering something in the life sciences. So pushing that forward instantly means that you see new things that you couldn't see before. This is why it's still fascinating to stay on the cutting edge of performance.
I think it
in microscopy
always has been as well. In the past I've described biology through the centuries as being the process of seeing in more detail since about the invention of the first microscopes, 400 years ago. John, what is the big challenge that's driving your work at the moment?
Nothing to do with microscopy. What I've produced in nanotechnology is a new set of tools, a toolbox, which you can use to design new instruments. And in the past, people have, we have Maxwell's equations, of course, but people use as a design tool something called Snell's law, which treats light as a stream of particles. Light isn't a stream of particles, it's a set of waves, and it doesn't consist of particles, it consists of electric and magnetic fields. And this new toolbox works in terms of the electric and magnetic field, so it's exact at the level of Maxwell's equations. What can we do with that? Well, we combine this new tool with another idea, which is a new class of materials, which are called metamaterials. Many things you want to do in optics are not possible because you don't have the material. If you want to build something, you've got to have a material with which to build it. The metamaterials are a new class of materials which introduce properties which have never been seen before in nature. And so you asked me what the next step is, and the next step is to exploit the design tools and the materials with which to build your design to go forwards into areas like, well, one thing I'm interested in is something related to microscopy, but actually light harvesting. So can you squash light into a volume much smaller than the wavelength? The wavelength of light is a bit less than a micron, a millionth of a meter, but if you could squash it into a billionth of a meter, a nanometer, then that will be a huge concentration. And the problems waiting for us there are, light finds it difficult to talk to atoms and molecules because light is normally as big as a micron, and a molecule is as big as 10 nanometers. And it's a conversation between a mouse and an elephant. But if you could bring light to the size of the molecular mouse, then that conversation would be a very informed one indeed, and you could sense single molecules. Something else which is a problem is we're in this room here which is full of light, and the light from different sources completely ignores the other source of light. Light doesn't talk to light, and that's very different from other particles. If you had electrons buzzing around the room, they'd scatter off one another very strongly. But you can make light talk to light if you push it into a square nanometer. And then you can switch light with light. You can compute with light. There are other things you can do, which is to throw light around the room, or this is being done now, not in terms of light, but there are other forms of radiation which these theories are relevant to. For example, it's the sort of radiation used in your cell phone, radar waves, to magnetic fields used in MRI. And all these areas of electromagnetism suffer from the same problems we had in understanding how to focus light. So from this problem of how to control light on a scale less than the wavelength has arisen all sorts of ideas across the entire spectrum. So, for example, one of the applications, one of the companies which has just been founded, is to control radiation going to satellites. So at the moment, if you're a reporter out in the desert, you use a satellite communications dish. It's heavy, consumes a lot of power. It's quite expensive, a few tens of thousands of dollars. But now, using the new design technology and the new metamaterials, this new class of materials, you can build a SATCOM receiver which plugs into the USB port of your laptop, which is about the size of a dinner plate and about as heavy, and which costs about $1,000. So that's the first sorts of applications which we're seeing from this. But I think that also makes another point about very fundamental technology. All of us had these basic ideas from which what we've been awarded from the prize for has grown many years ago. My first stirrings in this area were 10, 13 years ago. And it takes that length of time to actually produce what ultimately the public want to see, which is a product they can buy. And I think that's another message we should get to our governments, that patience, it takes time.
And starts with basic research. You know, of all the interviews that I've done over the years, the three of you say something, there's a subtext to everything that you say, which I've never really experienced in other scientists, which is you're really motivated by challenging things which seemingly are impossible.
Yes.
When you talk about squashing lights into a box, you talked about the Snell and saying, well, I've set out to show that that's not right. I feel like you're all slightly iconoclastic.
Yes, and we've suffered for it, I might say. Of course, all of us, as you heard about Stefan's work, Thomas's work also, and my work, we all had challenges when we were first producing our ideas. And actually, if you've not had that before in your life, it's quite upsetting to have people come up to you and say you're wrong and you're probably stupid as well, which people have done in all our cases.
It's kind of unfair.
But
comes with it.
what you come to realize after quite a short time is, I think Oscar Wilde said, if there's one thing worse than being talked about, it's not being talked about. and that's very true about a new idea, because the controversy attracts interviewers such as yourself, because you like to interview about personalities as much as science. And the personal fire which takes place tells other scientists, here's something really interesting. Here are some smart guys arguing one another because they don't really know what's happening. One of them doesn't really know what's happening. And that tells people that maybe not only is it interesting, but it might be profound as well.
Yes, dramatic conflict. Thomas, finally, what is the impossible challenge that you're working on next?
Well, I'm having a lot of fun right now, actually, the time of my life. And I'm coming back to what I wanted to do when I had these holes made some 20 years ago. And that is to make hybrid light matter. Hybrid light matter. So this is sort of convoluting matter and light in together to modify matter. This is not new, but the way I think I'm doing it is new. And the possibility is known. People have done that with atoms, in optics. But what I'm interested in is modifying materials and molecules by mixing in light into the state of the matter. And so the cherry on the cake in that case is that I don't actually need the light, the kind that we are looking at as illuminating us here. I can use something called vacuum fluctuations, which are electromagnetic fluctuations that happen all the time, everywhere. And that interacts with my material, just like light with what normal light we consider would do. And we actually change the properties of materials and molecules this way, and we've demonstrated this in a series of experiments. And of course, this again is producing skepticism in a lot of people out there, as Stefan knows. And so people come up to me and say, but that's impossible.
Yeah.
And I have referee reports that you get when you submit a paper that are longer than the paper that I'm submitting, with figures and everything, giving me lessons in physics or whatever else they're trying to convey. And it's okay. It takes forever to publish these papers because it looks like science fiction. But you know, that's part of nature. Nature sometimes is more bizarre than even scientists can imagine. And that's another attractive aspect about science, doing research. You know,
well, good luck with all of your impossible tasks.
Yeah.
I hope that one day they become possible. And congratulations on winning the Kavli Prize in nanoscience. Thank you very much.
Thank you very much.
Thank you.
Thank you.
Thank you.